This is problem 8 of the 2022 MMATHS Individual Round, and the problem reads, let S equals the set 1, 2, 3, 5, 6, 10, 15, 30. For each of the 64 ordered pairs AB of elements of S, AJ computes greatest common divisor of A and B. They then sum all of the numbers they computed. What is AJ's sum? Okay, so what AJ is doing is computing the GCD of every set of two numbers that comes from S. So like he'll find GCD of 1, 1, and then he'll add GCD of 1, 2, and so on and so forth. And then he'll add GCD of 1 and 30. Then he'll add GCD of 2 and 1, and notice the repeats, GCD of 2 and 2, and so forth. And while we could try to do that one at a time, it gets very tedious when there's 64. Instead, let's take a closer look at S, which really consists of I'm going to write these 8 numbers in sort of little different forms. So 2 to the power of 0 times 3 to the power of 0 times 5 to the power of 0. This is equal to 1. Then 2 to the 1 times 3 to the 0 times 5 to the 0, which is 2. 2 to the 0, 3 to the 1, 5 to the 0, which is 3. 2 to the 0, 3 to the 0, 5 to the 1, which is 5. Then we have 2 to the 1, 3 to the 1, 5 to the 0, 6. 2 to the 1, 3 to the 0, 5 to the 1, 10. 2 to the 1, 3 to the... Okay, excuse me. 2 to the 0, 3 to the 1, 5 to the 1, which is 15. And 2 to the 1, 3 to the 1, 5 to the 1, which is 30. And there has to be something special about this, right? Since these 8 numbers all happen to conveniently be just multiples of 2, 3, and 5, such that every prime shows up in their prime factorization between 0 and 1 times. But let me propose that we solve a similar problem, namely, ignore the 3's and just solve the problem for a set 1, 2. Then you only have to compare 4 GCDs. You only have to compute 4 GCDs, and that is very doable. GCD of 1 and 1 is 1. GCD of 1 and 2 is 1. GCD of 2 and 1 is 1. GCD of 2 and 2 is 2. So if you sum all these up, you get 5. That's fairly simple. We're gonna call this whole sum, we're gonna call it X equals 5, and that just signifies the case where there's only one prime. Now let's try to see what happens if we throw in a second prime, namely let's do 3. Okay, we have a set 1, 2, 3, 6. We want to compute GCDs of several things. In fact, we have 16 pairs if we can choose 4 for A and 4 for B. But let me sort of propose that we break these 16 up into groups of 4. The first group, you're going to be comparing GCD of A and B, where A and B are in the set 1, 2. The next group, we're going to do GCD of A and B, where A and B, well, okay, A is in 1, 2, B is in 3, 6, 3, 6. The third set's going to be where A is in 3, 6, and B is in 1, 2. And the fourth group before that we're considering is when both of them are in 3, 6. Now, if we consider this first group and we add the 4 GCDs up, we're going to get X. Or we could write 5. I'm going to write it like X because X is important. Because the GCD of 1 and 1 is just 1. The GCD of 1 and 2 is 1, etc., etc. Now, the second set where A is in 1, 2, B is in 3, 6. Like look at GCD of, for example, 2, 3. And no matter what A is not going to include a factor of 3. So the GCD of A and B will not have a factor of 3 as well. So you might as well just divide b by 3, and you will get the exact same thing. For example, GCD of 2 and 3 is equal to GCD of 2 and 1. Because essentially what GCD is we're just looking at every power of every prime and seeing whether or not both of the numbers have that prime in them or not. And in this case, none of the A's will have a 3 in it. So you might as well just look at GCD of 2 and 1 instead of GCD of 2 and 3. And similarly, GCD of 2 and 6 is equal to GCD of 2 and 2, simply because 2 does not have a factor of 3 in it. So you can just divide 6 by 3 and nothing's going to change. And using that logic, you really don't care about the 3's at all. So you can divide everything in this set by 3. And once again, you're going to get X as a result. Similarly, when A is in the set 3 and 6 and B is in the set 1 and 2, the 3's become obsolete. So you end up with X as well. Now, when A and B are both in 3, 6, this is where things get interesting. Because there's a theorem that says that GCD of K times A and K times B is equal to K times the GCD of the set AB. And why is this the case? This is the case because the GCD is essentially looking at factors of the two numbers. And when you look at KA and KB, they both obviously have K in them. So the GCD of KA and KB is what's common between these two, which is K plus some other stuff that's in A and B. And essentially what we can do is we can factor out a K just because both of them are divisible by K and talk GCD of AB instead. And by that logic, if A and B are both multiples of 3, we can just factor out a 3 from GCD of A and B. So for example, GCD of 3 and 6 is equal to 3 times GCD of 1 and 2. And since in this fourth case, every single pair A, B, both are multiples of 3, you can just factor out 3 and take GCD of A and B divided by 3. And because of that, your sum GCD of 3 and 3 becomes GCD 3 times GCD of 1 and 1. GCD of 6 and 3 becomes 3 times GCD of 2 and 1, etc., etc. Essentially, what you get is 3x in this case. So, all in all, this big mouthful with all of the 16 pairs sums up to just nothing but 6x equals 30. So we're going to let 6x, and we're going to call this new number y equal to 30. Because we're going to keep track of y with, we're going to keep track of this number 30 with y because it will be useful when we add our third and final prime, which is going to be 5. And when we have add our third and final prime, we can once again look at our set as 1, 2, 3, 5, 6, 10, 15, 30. And we can sort of split it into two groups, 1, 2, 3, 6, and 5, 10, 15, 30. And why do we do this? It's because once again, we have 4 cases where, and maybe I should give these sets names T1 and T2, where if you take GCD of A and B, you have A's in T1, B's in T2 as your first case, or should I say B's in T1 as our first case, A in T1, B in T2 is our second case, A in T2, B in T1 as our third case, and both in T2 as our fourth case. So in this first case, what are we going to have? We're going to have 16 possible sums of possible GCDs, and we're going to sum them up. But the catch is, if A and B are both in the set 1, 2, 3, 6, the sum of all of the GCDs of A and B is once again just going to be y, because we just calculated it. And by our same logic as before, if A is in T1 and B is in T2, that means that A is not a multiple of 5. So GCD of A and B is going to be equal to GCD of A and like 5C or something. But A is not a multiple of 5, so you might as well just get rid of the 5 because it's not going to be in any common factors. And suddenly you get that C is in the set T1 as well, because 5 times C is in the set B2, T2. And because of that, we get that if A is in T1 and B is in T2, the sum of the 16 things is once again y. And using identical logic, if A is in T2 and B is in T1, the sum of the 16 GCDs is in y. And finally, if A and B are both in T2, you're basically having GCD of A and B, well, A and B are both multiples of 5. So like, for example, if you have GCD of something like 10, 15, this is equal to 5 times GCD of 2 and 3. And you can factor out a 5 from every pair of A and B. And what you get but 5 times the sum of 16 GCDs, lo and behold, all of them fit into the T1 case, thus giving you 5y. So the sum of our 64 ordered pairs GCDs is nothing else but 8y, which is equal to 240. And this is our final answer, so we are done. Thanks for watching, and I will see you next time.